Вот. Почему-то вот именно этот шаг включить микрофон. Так, как теперь? Есть, да? Ура. Значит, можно начать. Okay, so we are now coming back to Fredholm operators. And our next goal will be to prove a useful criterion which characterizes Fredholm operators in terms of compact operators. This result is usually referred to as the Nikolski-Atkinson criterion. So our plan will be to prove this criterion and then to apply it to some properties of the Fredholm index. Okay, so here's the result. Before I give an exact statement, let me try to formulate the quintessence of this result. So the most important point is that an operator is Fredholm if and only if it is invertible modulo the compact operators. And this happens if and only if it is invertible modulo finite rank operators. So this is not the whole statement of the criterion, but this is probably the most important part of this criterion. And the full statement looks as follows. Theorem 1. Suppose that x and y are Banach spaces, and T is a bounded linear operator from x to y. Then the following conditions are equivalent. Condition 1, T is Fredholm. Condition 2, there exists a Fredholm operator S which acts in the opposite direction from y to x such that TST equals T and such that the operators 1 minus ST, this is an operator on x, and the operator 1 minus TS, this is an operator on y. So these operators are finite rank projections. Finite rank projections. That is, bounded projections onto finite dimensional subspaces. Property 3. There exists a bounded linear operator S from y to x such that ST is the identity map of x modulo the compact operators. And the same is true for TS. So this brief notation means that 1 minus ST and 1 minus TS are compact. 1 minus ST and 1 minus TS are compact. And any such operator S, of course I don't claim that it is unique. Obviously it is not unique because we can add any compact summand to S, and this new S will will have the same properties. So any such S is called an essential inverse of T. Any such S is called an essential inverse of T. In operator theory, the word essential usually means that some property holds modulo the ideal of compact operators. So S is an essential inverse, and T is essentially invertible if they are inverse to each other modulo the compact operators. Property 4, there exist two operators, S1 and S2, from Y to X, such that S1T is one modulo compact operators, and T S2 is also the identity map modulo the compact operators. So the difference between 3 and 4 is that here we have two operators. S1 is a left essential inverse, and S2 is a right essential inverse. Left and right essential inverses of T. So these four conditions are equivalent. And moreover, so some more information. If we know that T is Fredholm and index of T is 0, if T is Fredholm and the index of T is 0, then we can choose an operator T satisfying condition 2 such that this S is actually a topological isomorphism. And there exists a topological isomorphism. S from Y to X satisfying condition 2. And finally, if the operators S1 and S2 satisfy condition 4, S1 and S2 are as in 4, so S1 is a left essential inverse and S2 is a right essential inverse, then, well, then they are essentially the same in the sense that have the following relation. So the difference is a compact operator. Also, each of them is a two-sided essential inverse of T. Both S1 and S2 are essential inverses of T. Also, both S1 and S2 are Fredholm. S1 and S2 are Fredholm. And finally, the index of each of them is equal to minus the index of T. Okay, so this is the statement of our criterion. The criterion is usually attributed to Sergei Mikhailovich Nikolski. Strictly speaking, he proved this result only for Fredholm operators of index 0. He was mostly interested in operators of index 0. And a bit later, actually, a very similar argument was used by Atkinson. So Atkinson proved this result in full generality, that is for arbitrary Fredholm operators in 1951. Okay, so let's now prove this result. First we show that condition 1 implies 2. So if T is Fredholm, then there exists an operator S satisfying all these conditions. Well, T is Fredholm, so its kernel and its co-kernel are finite dimensional. We know that a finite dimensional subspace and a closed subspace of finite codimension are always complemented. This result was proved at the previous lecture. So since T is Fredholm, we conclude that the kernel and the image of T are complemented subspaces in X and Y respectively. And so we can find decompositions, topological direct sum decompositions. So X is the topological direct sum of X0 and X1. And Y is the topological direct sum of Y0 and Y1, where X0 is the kernel of T, Y1 is the image of T, and X0 and Y0 are finite dimensional. X0 is finite dimensional because it is the kernel, and Y0 is finite dimensional because it is isomorphic to the co-kernel. So they are finite dimensional. Okay, if I now restrict T to X1, then the resulting map T1 becomes a topological isomorphism between X1 and Y1. This is a topological isomorphism. Well, indeed, it is clearly bijective and bounded, and so the inverse mapping theorem shows that it is a topological isomorphism. Clearly, both X1 and Y1 are Banach spaces because they are topological direct summands of a Banach space, and the topological direct summand is always closed. So it is a topological isomorphism. So let's draw a picture which describes how our operator acts on the summands. So suppose this is X0, this is X1, this is Y0, this is Y1. So this is probably X1 and Y1 are big, and X0 and Y0 are small in the sense that they are finite dimensional. So T takes X0 to 0, because X0 is the kernel, and it takes bijectively X1 onto Y1. This is T1. So T1 is a topological isomorphism. So we have the inverse map from here to here. T1 inverse. And so let's now choose any linear operator from Y0 to X0. So take any linear operator S0 from Y0 to X0. So this is S0. And now we can construct the operator S we are looking for, which simply takes the direct sum of S0 and T1 inverse. And let's denote it by S. So S is S0 plus T1 inverse. So it acts from Y to X. And let's now show that S is indeed what we're looking for. First of all, it is bounded. It is bounded because both the summands are bounded, and we have the topological direct sum here. So we know that an operator from such a space is bounded if and only if it is bounded on each of the summands. So since this one and this one are bounded, we conclude that S is bounded. S is bounded because S0 and T1 inverse are bounded. And S0 is bounded because it acts between finite dimensional spaces. Well, clearly this condition holds by construction. If we look at the picture and apply T, S, and T, it's readily seen that this is the same as we just applied T. So by construction, TST equals T. Also, if we look at ST, first we apply T and then S. What we get is the identity map here and 0 here. So ST is the projection onto x1 along x0. ST is a projection onto x1 along x0. So if we now look at this operator, 1 minus st, we see that 1 minus st is a projection onto x0 along x1. So it is a finite rank projection because x0 is finite dimensional. And similarly, if we look at 1 minus ts, so ts is a projection. TS is a projection onto y1 along y0, and so 1 minus ts is a projection onto y0. Projection onto y0 along y1. And so we see that indeed 1 minus st and 1 minus ts are finite rank projections. So to complete the proof of 2, that is the implication that 1 implies 2, we have to show that S is Fredholm. Well, but we already know that T is Fredholm. And we also know that ST is Fredholm, because ST is a projection with a finite dimensional kernel. So T and ST are Fredholm. But we know that this condition implies that S is Fredholm. We know that if any two of the operators S, T, and ST are Fredholm, then so is the third one. So T and ST are Fredholm, and so S is also Fredholm. Okay, so we deduced 2 from 1. I'll probably keep the statement. It's more or less clear that 2 implies 3 and 3 implies 4. 2 implies 3 because, T, if S satisfies 2, then the same S satisfies 3. Any finite rank operator is compact. And clearly 3 implies 4. Oh, by the way, before we continue to deduce these properties from each other, let's look here. So let's now prove this extra result. So if T is Fredholm and the index of T is 0, then we can choose S such that it satisfies 2 and is a topological isomorphism. So if we're over index T is 0, then let's look at this picture. The dimensions of x0 and y0 are the same, because x0 is the kernel and y0 is isomorphic to the co-kernel. And so, before S0 was an arbitrary operator between y0 and x0. But now we can choose S0 in such a way that S0 is an isomorphism. There is an isomorphism. S0 from Y0 to X0. And if we look at the definition of S, we conclude that S is a topological isomorphism by the inverse mapping theorem. Clearly, it is an isomorphism because S0 is an isomorphism of Y0 onto X0, and T1 inverse is an isomorphism of Y1 onto X1. So S is a topological isomorphism. Okay. Well, as I have already said that 2 implies 3 and 3 implies 4. This is clear. So we now show that 4 implies 1. So if T is left, if T has a left essential inverse and a right essential inverse, then it is Fredholm. Okay, so S1T is 1 modular compact, so we can write S1T as 1 plus K1, where K1 is a compact operator on X. We know that this operator is Fredholm. This one is Fredholm. And since this operator is Fredholm, it follows that the kernel of T is finite dimensional. For the simple reason that it is contained in the kernel of S1T. And the subspace of a finite dimensional space is finite dimensional. On the other hand, TS2 is also 1 plus compact operator, 1 plus K2, where K2 is compact. 1 plus compact is a Fredholm operator by the Rhys theorem. This one is Fredholm. And this implies that the core kernel of T is finite dimensional. So the image of this operator is a subspace of finite codimension, and the image of T is even bigger than the image of this composition. So therefore, the image of T is also a subspace of finite codimension. And so the core kernel is finite dimensional. So we see that T is Fredholm. And we now know that all the 4 properties are equivalent to each other. And also we know that this one holds. Now to complete the proof of the criterion, we have to prove this part. So suppose now that S1 and S2 satisfy condition 4. Suppose that S1 and S2 satisfy condition 4. So again, we write S1T in this form and TS2 in this form. And we do the following trick. We look here and we multiply this equality by S2 on the right. And we see that S1 TS2 is S2 plus K1 S2. K1 S2. On the other hand, we can now look here and multiply this equality by S1 on the left. So we get the same operator, S1 TS2, but now we see that it equals S1 plus S1 K2. And finally, if we compare this and this, we conclude that S1, the difference between S1 and S2 is a compact operator. Because K1 and K2 are compact, so this one is compact and this one is compact. So this implies that S1 is essentially the same as S2. The difference is compact. Well, but this implies that S2t is S1t modulo compact operators. So the difference of these two operators is also compact, because the product of a compact operator by an arbitrary operator is compact. But this is, S1 is the left essential inverse, so this is 1 modulo compact operators. And we conclude that S2 is the left essential inverse of T. So S2 is a two-sided essential inverse. And similarly, we deduce that TS1 is 1 modulo compact. Okay, so S1 and S2 are essential inverses of T. I mean, two-sided essential inverses. We have to show that they are Fredholm, but we already know that 1 and 3 are equivalent. And we know that T is an essential inverse of S1, and T is an essential inverse of S2. So since 1 and 3 are equivalent, we see that S1 and S2 are Fredholm. Because each of them is essentially invertible. Okay, and finally we calculate the index. To calculate the index, we again come back to this equality. And we see that the index of S1t, is equal to the index of 1 plus k1. But again, the Rhys theorem states that the index of this operator is 0. 1 plus the identity operator plus a compact operator is a Fredholm operator of index 0. So this is 0, and by the additivity of the index, this is equal to the index of S1 plus the index of T. And so this equality implies that the index of S1 is minus the index of T. And if we do the same trick with this equality, TS2 is also 1 plus compact, we see that S2, the index of S2, is also minus the index of T. And this completes the proof. Okay, let's now deduce some useful corollaries of this criterion. To begin with, let's look once again at condition 3. Condition 3. In a special case where y equals x, this is very important special case where we consider operators on the same space. So if y equals x, then condition 3 can be written in a slightly more elegant way. I still keep the statement. So let's recall the following fact. Let's recall that K of x, space of compact operators on x, is a closed two-sided ideal of B of x. Of the algebra of all bounded operators on x. So we can consider the quotient B of x modulo K of x. And this quotient is a Banach algebra in a natural way. It is a unital Banach algebra. It is an algebra because the quotient of an algebra modulo a two-sided ideal is an algebra, and it's a Banach algebra because the ideal is closed. So it's a unital Banach algebra. And this algebra has a special name. It is called the Kalken algebra. Let's denote it by Q of x. The Kalken algebra of x. It's named after James Kalken, who was the first to study this algebra in detail. Have the following corollary of the Nikolski-Atkinson criterion. A bounded linear operator T on the bounded space X is Fredholm, even only if its canonical image in the Kalken algebra, T plus K, is invertible in the Kalken algebra. Well, the invertibility of this element is exactly our condition 3. The Kalken algebra plays an essential role in many analytic questions, especially in the case where X is a Hilbert space. And particularly, it plays an important role in the extension theory of operator algebras and in K-theory of operator algebras. And we will use the Kalken algebra in order to introduce a useful part of the spectrum of a linear operator. So suppose now that X is a bounded space over the complex numbers. And we give the following definition. We define the essential spectrum of a bounded linear operator T on X to be the following set. So sigma essential, the essential spectrum of T, is the set of those complex numbers lambda for which the operator T minus lambda 1 is not Fredholm. Is not Fredholm. So this is the essential spectrum. Clearly it is contained in the spectrum. Is contained in the spectrum because, well, an invertible operator is Fredholm. So if an operator is not Fredholm, then of course it is not invertible. So what can we say about the essential spectrum? Well, it's clear that if X is finite dimensional, then the essential spectrum is empty, because all operators on the finite dimensional space are Fredholm. And in the general case, we have the following corollary 2, which is a special case of corollary 1, which is immediate from corollary 1 actually. Corollary 2, the essential spectrum of T is nothing but the spectrum of its canonical image in the Kalken algebra. This is immediate from corollary 1. And we already know that the spectrum of any element of a unital Banach algebra is compact and non-empty. So this is compact and non-empty. And in particular, we conclude that this the essential spectrum is compact and non-empty. If X is finite dimensional. If X is infinite dimensional, of course. So this is a nice application of Banach algebra theory. There seems to be no direct way to prove that the essential spectrum is non-empty, which avoids using the Banach algebra theory. Okay. Our next goal will be to show that the Fredholmness, the property of being Fredholm, and the index of a Fredholm operator are stable under small perturbations. So, first of all, let's introduce some notation. From now on, we suppose that X and Y are arbitrary Banach spaces. not necessarily over the complex numbers, maybe over the real numbers, over K, where K is our base field. And we denote the set of all Fredholm operators from X to Y like this. This is the set of all Fredholm operators from X to Y, which of course are assumed to be bounded. And if X equals Y, we just write Fred of X. So our next result, Theorem 2, states that the set of all Fredholm operators is open. The set is open in the set of all bounded linear operators from X to Y. And moreover, the index, which is an integer valued function on here, is locally constant. Is locally constant. Or equivalently, we can just say that it is continuous. Because, well, the integers is a discrete space, and the function with values in a discrete space is continuous if and only if it is locally constant. It is constant in the neighborhood of each point. Before we prove this result, let's recall one more fact from Banach algebra theory, which was proved in the previous term. Let's recall that if A is a unital Banach algebra, then the set of invertible elements, we denoted by A cross, the set of invertible elements of A, is open in A. This is a useful result, which implies in particular that the spectrum is closed. So the set of invertibles is open. Let's now prove Theorem 2. So the proof of Theorem 2 will be divided into two, or maybe rather three steps. Into three steps. So the first step is lemma 1, which states that the set of Fredholm operators is open. The set of Fredholm operators is open. To show that it is open, let's assume first of all that it is non-empty. If it is empty, then there is nothing to prove. So we may assume that the set is non-empty. And then the Nikolski-Atkinson criterion implies that the set of Fredholm operators from Y to X is also non-empty. This follows from Theorem 1. So any essential inverse of a Fredholm operator is also Fredholm. So let's choose any Fredholm operators from Y to X. So we take any S, any Fredholm operator from Y to X, and consider the following map, as denoted by F, from the space of bounded operators from X to Y to the Kalken algebra of X, which takes T to the respective element corresponding to ST. So ST is an operator from X to itself, and we take it modulo the compact operators. So this is an element of the Kalken algebra. So it's immediate from this formula that F is a bounded linear operator, because the norm of ST is less than or equal to the norm of S times the norm of T. So F is also a bounded linear operator, so it is continuous. F is continuous. And let's now observe that the set of Fredholm operators from X to Y is nothing but the preimage under F of the set of invertibles in the Kalken algebra. Why is it so? Well, this is so because T is Fredholm if and only if ST is Fredholm. T is Fredholm if and only if ST is Fredholm. And ST is Fredholm if and only if this element is invertible. So we see that we have this equality. But, well, F is a continuous map, and the set of invertibles is an open subset of the Kalken algebra. And the preimage of an open set is open. So the set of invertibles of the Kalken algebra is open. And we conclude that the set of Fredholm operators is open. And this completes the proof of lemma 1. Lemma 2 is similar to lemma 1. It states that the set of all invertible operators from X to Y is open in the space of all bounded operators. Of course, we already know this in the case where Y equals X. If Y equals X, this is a special case of this fact, because B of X is a bounded algebra. And the general case is easily reduced to the case where Y equals X by the same trick as in the proof of lemma 1. So I leave the details as an exercise for you, but essentially the proof is almost the same as the proof of lemma 1. We take any bounded bijective operator from Y to X, now not Fredholm, but bijective operator from Y to X, and consider F from here to B of X, not to Q of X, but to B of X, which takes T to ST, and apply the same argument. Okay, we can now complete the proof of theorem 2. Proof of theorem 2. So lemma 1 shows that this set is open. So now we have to show that the index is locally constant. So let T be a Fredholm operator from X to Y. So we have to show that if we take an operator which is sufficiently close to T, then it will be also Fredholm and of the same index. We know that it is Fredholm because this set is open. But we have to show that if it is sufficiently close to T, then the index is the same. Okay, so as in the proof of theorem 1, we choose direct sum decompositions. So X is the topological direct sum of X0 and X1. and y is topological direct sum of y0 and y1, where x0 is the kernel, x0 is the kernel of T, y1 is the image of T, and x0 and y0 are finite dimensional. And let's introduce two operators. Let J denote the inclusion map of x1 into x. The inclusion map. And let P be the projection of y onto y1. The projection onto y1 along x0. Onto y1 along y0. If we now consider the composition, let's denote it by T1. T1 is P Tj. So this is an operator from x1 to y1. So clearly this is nothing but the restriction of T to x1. That is, it is the same operator T1 which appears in the proof of Theorem 1. This operator is a topological isomorphism. So its index is 0. Its index is 0. And by the additivity of the index, we see that this is the index of P plus the index of T plus the index of J. By the way, P and J are Fredholm by construction. J is Fredholm because it's injective and its co-kernel is x0, which is finite dimensional. And P is surjective and its kernel is y0, which is finite dimensional. So P and J are Fredholm. They are Fredholm. Okay. So if we now choose S, which is close enough to T, then PSJ will be close to PTJ. So the, more strictly speaking, we can say that the map which takes S to PSJ is clearly continuous. It is a bounded linear operator. So it is continuous. And now lemma 2 implies that there is a neighborhood U of T in the space of, in a set of Fredholm operators, such that for each operator S in this neighborhood, the operator PSJ is invertible. As an operator between x1 and y1. Because the set of invertible operators is open, so if S is close enough to T, this operator will be close to PTJ, and so it will be invertible together with PTJ. Okay, so it is invertible, and so its index is 0. Its index is 0. And again, by the additivity of the index, this is the index of P plus the index of S plus the index of J. And if we now compare this and this, we conclude that the index of S equals the index of T. for each s in this neighborhood. And so the index is locally constant. And this completes the proof. So we see that a small perturbation of a Fredholm operator is a Fredholm and has the same index. By the way, actually there are at least two ways of giving a precise meaning to the notion of a small operator. We can say that an operator is small if its norm is small. On the other hand, we can say that an operator is small if it is compact. So we have just proved that the Fredholmness and the index are stable under norm small perturbations. And our next goal is to show that they are stable under compact perturbations. Theorem 3. If T is a Fredholm operator from X to Y, and K is a compact operator from X to Y, then T plus K is Fredholm and has the same index. The index of T plus K equals the index of T. Well, this is actually a simple application of the Nikolski-Atkinson criterion. Let's choose an essential inverse of T. So we choose an operator S from Y to X such that ST is 1 plus a compact operator, and TS is also an identity map plus a compact operator. So S is an essential inverse of T. And now it is now very easy to observe that the same operator S will be an essential inverse for T plus K. Because if we multiply S by T plus K, this will be ST, it is 1 plus K1 plus SK. And this sum, these two sums are compact. And similarly, T plus K multiplied by S is TS, which is 1 plus K2, 1 plus K2 plus KS. And this one is compact. So we conclude that S is an essential inverse for T plus K. And theorem 1 implies that T plus K is Fredholm. Okay, so this operator is Fredholm. Let's also recall that in theorem 1 we proved that the index of the essential inverse, the index of S, is minus the index of T. So the index of S, on the one hand, it is minus the index of T, but on the other hand, it is minus the index of T plus K. For the same reason, for exactly the same reason. And we see that the index of T equals the index of T plus K. And this completes the proof. And finally, as our final application of the Nikolski-Atkinson criterion, let's give a useful characterization of Fredholm operators of index 0. This result is due to Nikolski. So if T is a bounded linear operator from X to Y, then the following conditions are equivalent. Condition 1, T is Fredholm and the index of T is 0. Condition 2, T is a compact perturbation of a topological isomorphism. T can be written as R plus K, where R is a topological isomorphism from X to Y, and K is a compact operator. And finally, part 3. Part 3 is the same as part 2, almost the same as part 2. So it is of the following form, where R is a topological isomorphism from X onto Y. And K is a bounded finite rank operator. K is a bounded finite rank operator. So let's recall that script f of xy denotes the set, the space of all bounded finite rank operators from X to Y. So this result characterizes Fredholm operators of index 0. So let's show that one implies 2. Suppose that T is Fredholm and the index of T is 0. Let's recall theorem 1. When we proved theorem 1, we have also proved that there exists an essential inverse for T, which is a topological isomorphism. So this is true for any Fredholm operator of index 0. There is a topological isomorphism S between Y and X, which is an essential inverse for T. Actually, we only need that S is a left essential inverse for T. One plus K1, where K1 is a compact operator on X. And now we just multiply this equality on the left by the inverse of S. So this implies that T equals S inverse plus S inverse K1. So this summand is a topological isomorphism, and this summand is compact. And that's it. So it is the sum of a topological isomorphism and a compact operator. Well, it's clear that 2 implies maybe this is not the optimal way, sorry. The optimal way is, fortunately, it is almost the same as my argument. The optimal way is, of course, to deduce 3 from 1, because then we can obviously see that 3 implies 2. So to show that 1 implies 3, we again we recall the statement of theorem 1, and let's recall that there is a topological isomorphism with this property such that K1 is a bounded finite rank operator. This is property 2 of theorem 1, and such an isomorphism exists. And now, if we look at T, we see that T is the sum of a topological isomorphism and a bounded finite rank operator S inverse K1. So clearly, the composition of a finite rank operator with an arbitrary linear operator is also a finite rank operator. Okay, now it's obvious that 3 implies 2, because the finite rank operator is compact. And to show that 2 implies 1, we suppose that T is of this form, and we recall theorem 3, which states that a compact perturbation of a Fredholm operator is a Fredholm operator of the same index. But R is a topological isomorphism, so it is a Fredholm operator of index 0. So we simply apply theorem 3. And we conclude that T plus K is also R plus K is also a Fredholm operator of index 0. Okay. So I hope you agree with me that this theory is rather nice and elegant, but maybe a little bit too abstract. So our next goal is to discuss an illustration of this theory, or an application, and to deduce a nice geometric formula for the index of a Toeplitz operator on the unit circle. Toeplitz operators. So let's introduce some notation. As usual, by bold T, we denote the unit circle on the complex plane. And we will work with the space L2 on the circle, which is the usual L2 space of square integrable functions with respect to the canonical measure on the circle, where the measure is the normalized length measure. It is the length measure over 2 pi. So that the measure of the circle is 1. This space L2 of T has a canonical trigonometric basis. So for each integer n, we denote by En the map from the circle to itself, given by the following simple formula. En of z is z to the power n. And let's recall the Weierstrass approximation theorem, the classical result from Fourier analysis, which states that the linear span of these functions En, this is nothing but the set of all trigonometric polynomials, or if you like, the Laurent polynomials on the circle. So this subspace is dense in the space of continuous functions on the circle. By dense here, I mean, of course, uniformly dense. Dense with respect to the supremum norm. This is the Weierstrass approximation theorem. Hence, this result implies that if we consider this set in the set of all Ens in the L2 space, it is an orthonormal basis. M is an orthonormal basis of the big L2 space. It's easily seen to be orthonormal, and the Weierstrass theorem states that it is dense in C of t. And since C of t is dense in L2, we conclude that this linear span is dense in L2. So it is an orthonormal basis. We now define the Hardy space. The Hardy space on the circle as follows. So this is the closed subspace of L2, denoted by H2, which consists of those elements in L2 whose negative Fourier coefficients, that is, Fourier coefficients with negative numbers, vanish. This is 0 for each negative n. And since En is an orthonormal basis, this is equivalent to say that this is just the closure of the linear span of the elements En, where n is non-negative. So this is a closed vector subspace of L2. So we can consider the orthogonal projection. We'll let P denote the orthogonal projection of L2 onto H2. onto H2. So this is the projection onto H2 along its orthogonal complement. This is the so-called Rhys projection. It is named after Marcel Rhys, who was a brother of Friedrich Rhys. And we know that Friedrich Rhys was the father of the theory of compact operators. And Marcel Rhys was also a quite famous mathematician, but not so famous in functional analysis as mostly in function theory and in harmonic analysis. We're now almost ready to introduce Toeplitz operators. So some more notation. So for each essentially bounded measurable function f on the circle, we let mf denote the multiplication operator by f acting on the L2 space. The multiplication operator. So we define the Toeplitz operator, with symbol f as follows. First, we restrict MF to the Hardy space, but in general, there is no reason for the Hardy space to be invariant under the multiplication operator. So we restrict the multiplication onto the Hardy space, and then compose it with the Rhys projection. And what we get is an operator on the Hardy space. This is P MF restricted to H2. So this is a bounded operator on the Hardy space, and it is called the Toeplitz operator with symbol f. So we will be interested in the special case where the symbol is a continuous function. And our goal will be to show that if f is continuous and no row vanishing, then the respective operator, Toeplitz operator, is Fredholm, and to calculate explicitly its index. So we will need the following auxiliary proposition. First of all, for each continuous function f on the circle, the commutator of the Rhys projection with the multiplication operator mf is compact. This commutator is compact. And part 2, if we take two continuous functions, f and g, the Toeplitz operator with symbol fg, well, it is not exactly tf/tg. In general, this is not the case. But this equality is true modulo the compact operators. Well, to prove this result, we do the following. We denote by A the space of those functions, of those continuous functions on the circle, for which this result is true, for which the commutator of P and MF is compact. So our goal will be to show that A is actually the whole of S of, or the whole of C of t. But anyway, it's clear from this definition that A is a closed vector subspace of C of t. A is a closed vector subspace. Well, it is closed because clearly the map which takes F to this commutator is continuous. It is a bounded linear operator. And the space of compact operators is closed. So F A is the preimage of a closed set under a continuous map. So it is closed. And clearly it contains the function which is identically 1. If F is identically 1, then MF is just the identity operator, which commutes with everything. I claim that A is actually a subalgebra of C of t. To show that A is a subalgebra, we observe that if F and G are in A, then the commutator of P with MFG, well, M of G is of course MFMG. This is clear. And the commutator in any, with a fixed element in any associative algebra is a derivation. So we have the following formula. So the commutator is a derivation. So we have this. But this commutator is compact. And this commutator is also compact. And by looking at this formula, we conclude that this commutator is also compact. So A is a unital subalgebra in C of t. This is a subalgebra. And finally, to show that A is actually equal to C of t, so it is closed, a closed subalgebra. To show that it is equal to C of t, it suffices to show that it contains all trigonometric polynomials, because the space of trigonometric polynomials is uniformly dense. And since it's a subalgebra, it's enough to check this condition only for E1 and E minus 1. But if we look at ME1 and calculate this explicitly, it's very easy to show that this operator acts on our basis as follows. It takes E minus 1 to E0, E minus 1 to E0, and other elements of the basis go to 0. This is a little exercise for you, a very easy explicit calculation. So we see that this is a finite rank operator. It is a rank 1 operator. Its rank is a one-dimensional space. So this implies that E1 belongs to A. And a similar argument shows that E minus 1 also belongs to A. And now, since for each positive n, En is E1 to the power n, and E minus n is E minus 1 to the power n, we conclude that since A is a subalgebra, we see that all elements En belong to A for each integer z. And now the Weierstrass theorem implies that A is C of t. And this completes the proof of part 1. So this commutator, the commutator of the multiplication operator with the Rhys projection, is always compact. And part 2 is a simple corollary of part 1. Well, indeed, what is TF-TG? Well, by definition, this is PMF, PMG, restricted to the Hardy space. But now, if we look here, MFP, we can interchange the summands, the factors MF and P, modulo the compact operators. So by part 1, this can be written as P, M, F, M, G, modulo the compact operators. PP is P because it's the projection, MFMG is MFG. But this is nothing but the Toeplitz operator T of G. Okay, so this completes the proof of our proposition. So in conclusion, I'd like to mention that part 2 of this proposition means the following. Part 2 means that we get a homomorphism from the algebra of continuous functions on the circle to the Kalken algebra, map from C of t to the Kalken algebra of the Hardy space. So this map takes f to the respective Toeplitz operator with the symbol f. And part 2 says, means exactly that this is an algebra homomorphism. An algebra homomorphism. Okay, so that's all for today. And in the beginning of the next lecture, we apply this observation to an explicit index formula for Toeplitz operators. So we will see that for each nowhere vanishing function f on the circle, the respective Toeplitz operator is Fredholm, and its index is equal to minus the winding number of the respective loop around 0. Okay, thank you.